Um, Hello, everyone. It is my pleasure to introduce Klaus Paschek, a PhD candidate at the Max Planck Institute for Astronomy in Heidelberg. His research explores the geochemical and planetary processes that could have enabled life's building blocks to form on the early Earth. Today, he will speak on the deep mantle-atmosphere coupling and the carbonaceous bombardment, options for biomolecule formation on an oxidized early Earth. Before we begin, you can ask questions after the talk, and if you would like, you can also write the questions in the chat and they will be answered after the talk. So, floor is yours now, Klaus.
All right. Thank you very much for this kind introduction. And of course, hello, everyone. I want to explore with you today together how the early Hadean Earth, which, as you can see in this artist's impression here, was probably a rather hostile environment, might actually have been a key step to prepare the building blocks of life. And especially, we want to understand how we can also, how this can be possible even on an initially oxidized atmosphere or an initially oxidized Earth atmosphere. And then we want to see how we can get to a situation which looks a bit more like this. You might immediately find this much more inviting. The hydrosphere has settled now already and the temperatures have cooled off. And then, for example, here on the left-hand side, we have a freshwater pool at the first land masses which have emerged from the oceans. And maybe you might fancy to have a little swim in there. And maybe life had exactly the same idea. So when we want to talk about the building blocks of life, we have to talk about prebiotic chemistry. And there I probably don't have to repeat this. Most of you will be familiar with the very famous Miller-Urey experiments, where in this apparatus here we see on the right hand side, in a reducing atmosphere with spark discharges, it was possible to form in a residue which formed at the bottom a plethora of building blocks of life, including at the beginning amino acids, but there are also more modern versions of the experiment which include building blocks of RNA and DNA, nucleobases, and also under different conditions. But the key takeaway here is that we need reducing or at least mildly reducing conditions to make this possible. Under oxidizing conditions, there is no way to make these building blocks in this way. And just to get everyone on the same page, so the molecules I want to focus on here today are the building blocks of RNA and DNA. So we have in this left box, in the red box, we have the nucleobases, which are the genetic letters, the code of our RNA and DNA molecules in all life as we know it. And then you'll also look at the sugar ribose, which then together with phosphates builds the backbone of RNA molecules, which leads us then to one among, I'm aware there's also other theories of how life have started, but the RNA world is one of them, as RNA was shown to have kind of self-catalytic activity. There were some experiments showing that RNA can polymerize its own formation or its own strand formation, which kind of gives a self-consistent system, kind of one of the first features of what one could dare to call a life. And now we have to understand, do we have reducing conditions on the Hadean Earth? And the first takeaway here is the Hadean Earth is the big unknown. We don't know so much about it. And we also have to very much care about the timescales involved, because when you talk to a geophysicist or geologist, they usually show you this kind of graph, and the geologists are usually interested in the last 500-ish million years, because this is where the fossil record starts here at the beginning of the Cambrian. But we actually want to go much deeper, and we can look at a graph which looks a bit more like this, which gives us in a linear relationship. We see that everything that you saw so big in the previous part is only these last few sections here. But we can see here in this purple line that life probably started very much further in the past, somewhere at the border between the Hadean and Archean. And so we have to understand, how was this even possible? How was this in first assumption hostile Hadean able to prepare the stage for life to emerge? And as I say, the timing matters a lot, because we know a lot more about the Archean, but it's not always so easy to just extrapolate this to the Hadean. I often see this in the scientific literature. Please don't do this. Beware of this, that this is still a much different time. when we look at, so we have here in this graph, we have kind of an outline of the different processes. So we go all the way from the planet formation of the Earth, then to the moon forming impact as kind of still big milestone event, to then the kind of first crust formation. And then we also have the late heavy bombardment or also late veneer. We will also talk about this in a second. And then in the bottom, we have outlined then the first traces of life. When we actually look in the rock record, the oldest rocks that are preserved are only present from the Archean up to 3.8 billion years ago in the greenstone belts, which we find, for example, in South Africa and also in Canada and Australia. And we can then look at the oxidation state of these rocks. And I will just throw here some keywords for the experts who might appreciate this, but we don't have to go into much detail there. This is then usually characterized by the oxygen fugacity of different mineral buffers describing the redox state of our rocks and minerals. And in very first assumption, this is mostly about the balance between ferrous 2 plus iron and ferric 3 plus iron. This is the two different valence states, and 2 plus is more reducing and 3 plus is less reducing or more oxidizing. And this will then determine the volcanic outgassing that we should expect from the early Hadean Earth. And there's then these different buffers that are defined in the literature. And so when we look at the greenstone belts, then the signatures found there from the Archean are rather oxidizing, which is a bad news for us. There are also some zircons, which is a very sturdy mineral, which survived all the way back, which originated all the way back to the Hadean. And also there are some claims of some oxidizing signatures. There are actually some pitfalls to zircons and what part of the Earth's mantle and crust they actually probe, but we can talk about this maybe in the discussion in the end. The big takeaway is that we have kind of this dilemma arising that at least from first assumption from silicious volcanic outgassing, we would expect oxidizing gases, whereas, as you might remember, for our pre-body chemistry, we need reducing conditions. And so how can we solve this problem on the Hadean Earth? For this, we have to understand the Earth as a system, as a whole, with all different processes which are acting on this early planet, on this young planet. And as a first step, we will dive into its interior. You see here this cross-section, and we have to understand the convection in the mantle, and then the first maybe plate tectonics that starts to arise, and then especially the interaction of this mantle with the hydrosphere, which leads to the formation of these hydrothermal vents. And we will especially focus on the white smokers, which are driven by serpentinization, which is a chemical reaction. But more detail about this in a second. So when we look at the Hadean mantle and how it is evolving, the magma ocean starts to freeze up from the bottom to the top. And it's very important to note that a lot of water, this is also kind of the current trend in the scientific literature, that a lot of water is actually mixed into the interior of the Earth because it has a higher solubility in comparison to CO2, which was in this magma and gets displaced, kind of pushed out to the surface, forming a first primary atmosphere of up to 200 bars, depending on which model you believe in, of a really thick CO2 atmosphere. Then the big question is, was plate tectonic first, was it even active in the Hadean? And then how much was it active? This is also an ongoing debate. I don't want to dive too much into detail. I just picked two recent studies here, which also look again at zircons and different signatures in them. And they are both Nature papers from 2 years ago, and one says clearly yes, one says clearly no, so we don't really know. But when we assume that plate tectonics was active, then we have this also subduction process at the plate boundaries, and especially we have also these diverging plate boundaries, which we need for the formation of our hydrothermal vents that we then will be interested in. And the idea is then actually that when plate tectonics starts to work, we can actually flush the CO2 very efficiently again out of the atmosphere into the interior of the Earth. And because we have participating settling carbonates, which get then flushed by subduction into the mantle and can remove these 200 bars very efficiently. And for example, the model we were orienting us on says this can happen in only 160 million years, but also other models are also agreeing with this. Then we have to understand that the Hadean mantle was probably very different from what we have today on Earth. So because of this, when we look at the present day Earth, which is kind of in this left side of this slice here illustrated, we have a rather thick crust which sits on top of a very homogeneously mixed convecting mantle at the bottom. Whereas because of this strong water mixing in into the D mantle, we might have a much thinner crust which sits on top of a very heterogeneous demixing mantle, which allows then for a lot of this ferrous reducing iron to well up, and we might then think about ways to exploit this reducible potential for our periodic chemistry. And at the diverging plate boundaries, as I said, we have then hydrothermal vents, where we have then water seeping from the ocean into the crust, interacting with this magma, which is rising up from the mantle, which gives rise to the so-called white smokers, which look like this. This type of hydrothermal vent is completely driven by chemistry, not by classical, eruptive magma silicate volcanism, but this is purely chemical reaction, which gives rise to these white plumes. And these are generated by the so-called serpentinization reaction, which is the reaction of olivine with water. And of course, the involved minerals are much more complicated than what I have illustrated here. But the rough idea is that we transform this ferrous iron into the ferric iron, and the reducing potential goes into the production of hydrogen gas. And then we form serpentine. And due to these high pressures in this hydrothermal system, we have CO2 also supplied from the magma, which can then interact at these high temperatures and pressures and this is actually good because, right, we want to make organics. We need a carbon source so we can exploit CO2 for its carbon and transform it into a more reducing form, which is methane. And what we then actually do in our simulation is that we then use real measured ratios between the hydrogen and methane emissions that were actually probed by submarine missions, and they directly probe these fluids. And we will then use this to inform our model. And the idea is then that we have these hydrothermal vents which then emit these gases to the atmosphere, and we will then be very much interested what this can do for our atmosphere chemistry. Another parameter that we have to talk about is the so-called hydrothermal circulation depth. This is simply said just how deep the water is penetrating into the crust. Because you can imagine the deeper we go, the more iron the water gets in contact with, which will then boost serpentinization and gas emission in the hydrothermal vents. And when you want to understand how deep might this water penetrate in, we can, of course, first do the direct sampling just by drilling in, just taking a big ship with a big drill, drive out to the ocean and just drill down into a mid-ocean ridge where we find these hydrothermal vent systems. And there was, for example, one study by Alt and Tiegel where they looked at carbonate deposits. This is exactly what I said before, that we have carbonates which are deposited by the inflowing water, being a direct indication of aqueous activity in this rock. And they found in the drill core that at least up to 500 meters deep, they find them, and they even indicate there should be traces up to 5 kilometers, even on present-day Earth. Then there was a very recent study, which I found very interesting. This was by Lissenberg et al. From last year. They just also drilled in and just directly looked at serpentines and trying to find them. We see here at the bottom the picture where we have Harzburgite and Dunite, which are different degrees of serpentine. And they say also that up to these 1.2 kilometers that they drill down, they still find almost 100% serpentinization, which we see here on the right-hand side in this graph here, where the extent of serpentinization is indicated. And then the last proxy we can use are seismic waves. When there is an earthquake somewhere on the Earth, then these seismic waves are traveling through the interior and allow us to kind of have a look inside by then recording them at different stations at the surface, and especially we can have a look at the velocity change or the velocities and how they change as they pass through different layers in the Earth's crust and mantle. And there's this characteristic velocity change, which indicates the transition from serpentine to then further down mantle material, which should go down to at least 3 to 4 kilometers. And when we push even further to the Hadean, there are also some theoretical simulations by Korinaga, for example, where it is predicted that, especially in this very violent early Hadean Earth, with very fast plate speeds and strong overturn in the interior from the mantle convection, it was predicted that there could be cracks going down into the crust and mantle up to 30 or even 50 kilometers down, which would then again allow the water to seep in and serpentine and drive our serpentinization. Then another process we have to talk about is bombardment from space, because meteorites, when they hit onto the Earth's surface, they also interact with the hydrosphere and atmosphere and can also lead to the emission of reducing gases, which can be interesting for our pre-body chemistry. And for that, we first have to define what the late veneer is. The late veneer term is coming from the geosciences, I would say. Well, the idea is that we found an excess, we found too much of siderophile elements in the crust of our Earth. Siderophile elements are iron-loving elements, which usually during the differentiation process, as our Earth forms, should sink into the core. But after the Earth has already finished forming, there has to have been another bombardment with undifferentiated, probably chondritic material from outer space to explain why we have this excess of siderophile elements in the Earth's crust. This is why the term late veneer being laid around our Earth. When you go to when you come more from the astronomy side, then you might know this as the late heavy bombardment. Of course, these are not exactly the same things. The definitions are slightly different, but there's also the idea that there was a kind of delayed strong bombardment of material after the main formation process of the Earth was already finished. And then one can base these as like how much was the flux of material. This is usually based on the lunar cratering record. And here we see for different epochs, one at the very beginning of the Hadean and one more in the end, and the border to the Archean. We see different scenarios of how this bombardment slowly declined over time. And for example, these red stars are then kind of an intermediate way that we use for most of our simulations. But we also tested some extreme cases with the maximum bombardment. You can find this all in this publication. And then, of course, we have to talk about what material is actually falling in there. So we have on one hand, we have the enstatite chondrites, which are more iron-rich, which probably formed in the more inner regions of our forming solar system. And then on the other hand, we have the carbonaceous chondrites, which, as the name suggests, contain a lot of carbon. And they probably formed in further outer regions, somewhere close to the water snow line, probably, as our solar system was forming. And then there's actually still a big debate going on in the scientific community. What material was it now? Which one was the dominating, or was it even only one or the other? This is changing all the time. I brought two examples here on the right-hand side. We see here they are looking there at these siderophile elements, and then at this excess and how to explain the present-day Earth's composition, which is given here in this black diamond. And they actually claim to have found some kind of unequilibrated mantle, which actually was somewhere from the Archean. And this actually lays on the opposite side of carbonaceous chondrites. So they actually suggest that only by mixing this with carbonaceous chondrites in the late veneer, we can actually arrive at a present-day Earth. But actually, you might be aware, some of you, in the further past, it was mostly camp enstatite. And these are no more recent ideas, but there's again new claims again for enstatite. I also found a very interesting paper, which is on the left-hand side by Hopp et al., where they actually show by looking at molybdenum isotopes that actually none of them completely alone can explain the late veneer, and only a mixing between these two reservoirs is actually allowing us to arrive at present-day Earth in the middle here in green. What we then did is we just looked at different scenarios, one with only enstatite, one with carbonaceous, and also with mixing of both reservoirs, and see what this can do then for our atmosphere chemistry on our early Earth. Because then for enstatite bombardment, the idea is fairly similar to what we have just discussed for the serpentinization. We again bring a lot of ferrous iron-rich material onto the Earth's surface, which interacts with the hydrosphere to again lead to emission to hydrogen gas. And I just list here a few studies, very recent studies, which looked into this effect of how this bombardment can influence atmosphere chemistry and maybe even prebiotic chemistry. On the other hand, we have carbonaceous bombardment, and there's the idea that the carbon that we bring in can actually interact with the nitrogen and the water in the atmosphere and hydrosphere to directly form hydrogen cyanide during this impact shock event. And this is based on some experiments which were performed by a Japanese group, Kurosawa et al., where they literally just shot a projectile onto a graphite sample and then looked into the plume that was emerging from this kind of impact shock explosion. And they found that under nitrogen water atmosphere, they find up to 2.8 mole% of the carbon is directly converted into hydrogen cyanide. And though, of course, you have to think about that CO2 might also have been a significant component on the early Earth. And they actually tested for this. And they found that as long as we have more nitrogen than CO2, this reaction is still in operation. And here's then the data that we then use for our simulation, where we basically, as we reduce the amount of CO2 in the atmosphere, we get more and more efficient until we get over a threshold. I think it's 1 or actually 3.35 is the actual ratio, and then we have full HCN production efficiency. So now we talked about all these reducing gases, which are emitted from different sources on the Earth, and now we want to bring them into the atmosphere and look what is actually happening with them there, because these gases are then subjected to UV radiation from the early sun, which allow to in the upper atmosphere layers to split these molecules into radicals, which can then recombine into new molecules. For example, also hydrogen cyanide as one potential key precursor to prebiotic molecules. And this is based on a previous study, which was compiled by Ben Pierce et al., where they looked at all these different sources, and what we now specifically added on top is to have the serpentinization, the emission from the hydrothermal vents, to be in an accurate way for the Hadean Earth, because the Hadean was probably very different from what we have today. And we also on top newly bring in this carbonaceous bombardment and its effect on the atmosphere. And this previous model is a combination of the Petit-Radrans code with a chemical code to then have a whole suite of chemical reactions which are then happening there, where the rough idea is, of course, overly simplified again. These molecules get split by the UV radiation and can form via several intermediates, for example, hydrogen cyanide, but we also actually have formaldehyde in the code, which includes up to 260-ish reactions which are happening there in the atmosphere. Here are the results now for these atmosphere simulations. So first, for you to understand, we have in this area of plots on the left, in the left column, we have results which come from an initially reducing atmosphere, whereas on the right-hand side, we have an initially oxidizing atmosphere. And then we of course also have to talk about this hydrothermal circulation depth in our geological scenario, where at the top we have 500 meters, and you see we actually went still rather conservative, as you might remember from what I discussed before, and only went up to 2 kilometers of hydrothermal circulation depth and serpentinization. And then we can now look at the evolution of these gases over time in the atmosphere. And I highlighted here our kind of key molecules of interest, which is methane, which is a key also intermediate to be transformed into hydrogen cyanide. And as we might expect in a reducing atmosphere, we have fairly stable and consistent abundances of molecules, of these reducing molecules in our atmosphere. Whereas when we go to the oxidizing case, and this might not be surprising, we see after some time a sudden increase of oxidizing gases, which lead to a strong decline in these reducing gases, which leads to many orders of magnitude less amounts for them, which is of course fairly bad for our potential to have prebiotic chemistry happening. But and this is now a big new finding in the study is that when we increase the circulation depth down to 2 kilometers, we see that although we start, and this is really important now to note, with an initially oxidizing atmosphere, we still can pump so much hydrogen and methane into the atmosphere that we can completely stop this oxidation of the atmosphere and completely reverse it into a reducing one, which leads then again to many orders of magnitude higher hydrogen cyanide and also formaldehyde abundances in our atmosphere simulations, which is very exciting and good news for prebiotic chemistry. So overall, we can say that because of course the geological processes directly provide methane, they dominate the methane abundances in the atmosphere, which then in turn dominates hydrogen cyanide, which is then formed from that. We also did other simulations. I just spare you details, but they look fairly similar to what I have just shown you here, where when we have also this bombardment then happening, especially when we have carbonaceous bombardment, then this is the, because it's also directly supplying HCN, this is then also strongly dominating the HCN abundances in the atmosphere. But the key takeaway here is that serpentinization alone with only 2 kilometers of hydrothermal circulation depth can completely convert this oxidizing into a reducing atmosphere. And the idea is then that later this HCN and also formaldehyde can rain out from the atmosphere and then participate in some pre-body chemistry, which we will talk about in a bit. But first, I will compare this to other recent studies. This is from the Zahnle group by Vogan and colleagues, where they mostly focus on big anstatite impactors and the aftermath of then the Earth's atmosphere and also hydrogen cyanide production. And they actually run into a problem as because they make everything directly from H2. They start to form at some bombardment intensity level. They start to form hydrogen hazes, which actually start to render the Earth uninhabitable. Especially also the temperatures rise here to 380 Kelvin and above, which also are temperatures where RNA is unstable. Whereas in our model, we even with our only serpentinization active, we have already hydrogen cyanide rain out rates, which are more than an order of magnitude more than what they found. And especially we don't run into this temperature problem. Because when we have our geology active, we have kind of the shortcut of directly going to methane emission, which can then lead immediately to high HCN abundances, and we don't have to go start all the way from H2. And with carbonaceous bombardment, we can push this even further because, I mean, we just directly introduce HCN into the system. Now, the idea is that, yes, these molecules have formed there, and now they are rained out onto the surface, onto the first rising land masses. You can imagine something like hotspot volcanism, like volcanic islands like Hawaii or Tenerife, for example, where the idea is that we have then surface ponds where this material is raining in and can then undergo so-called wet-dry cycling. Because in this goes back all the way to Darwin, this idea of the warm little pond, where the idea is that this actually can drive prebiotic synthesis, especially because some of these reactions need the removal of water, which is of course inefficient when you are in water solution. But by drying it down, these activation barriers in the reactions can be overcome, and a plethora of different prebiotic molecules can form. For example, the building blocks of RNA, but also you can also talk about amino acids and peptides. And so the idea is that, the idea is that we base this all on actual experimental yields. So we don't invent any formation yields. We all base this on experimental literature. We also added in this study we added a new formation rate for ribose, which was kindly provided by our chemistry colleagues Oliver Trapp at LMU in Munich, and especially his student Kai Kohler, who performed the Formose reaction for us to make ribose, and they gave us then a formation yield that we also directly then use in our simulation code. And here we see the result, in this case, for when we have our carbonaceous bombardment, also in an initially reducing atmosphere, so the best case scenario. And we see in this typical cycling behavior of the concentrations, in this case then of adenine in our Darwinian pond. And here on the right-hand side, we see the HCN levels as they are raining in. We also have formaldehyde in there. And then we also have ribose abundances, which are given here in this blue dashed dot line. Now, what I want you to focus on here in this result, this is now especially when we look at this specific curve, this pinkish one here, this is now an initially oxidizing atmosphere, slowly driven by serpentinization and hydrothermal vents. And again, we look at the adenine abundances over our wet-dry cycles. And we can see that the abundances here actually peak. And this is now also for the very first time we are able to show, because in this shaded area here at the top is what is actually required as the minimum abundance to have nucleoside formation. So the actual monomer building blocks of RNA. I will also talk about this more in a second. And we now, for the very first time, are able to actually motivate abundances for adenine, for example, which are actually sufficient to get over this threshold to really get the RNA world going, so to say. Because before there was always a big gap between what chemists say we require as the least amount for me to show that this actually works, in comparison to what, for example, geophysicists and physicists were able to motivate by what the early Earth's environment was actually able to supply. But we actually now finally solved this problem and showed that even in initially oxidizing atmosphere, we can have enough reducing potential to really push towards an RNA world, for example. We also see again the HCN abundances, and also we have then several orders of magnitude higher ribose abundances as well. And so we can compare this to what in recent studies was at least required for nucleobase and ribose abundances to have the formation of nucleosides, and then with phosphate together nucleotides, which then make up our RNA and DNA molecules. And we can now confidently say, yes, we can actually motivate enough abundances for this to actually be possible, which is very great news. And this leads me already to my take-home messages. So meteorites can, of course, also deliver biomolecules, which have formed already in space or also then in their parent bodies. But especially during impact, they also have the potential to directly generate a lot of reducing potential that we can exploit for prebody chemistry. And especially the main takeaway is that serpentinization alone might have been on the Hadean Earth, especially in a scenario that is really considering the Hadean as it probably was, especially different from what we have today, that this can stop this oxidation of the atmosphere and in letting us to the conclusion that the early Earth was probably good in cooking up quite a potent prebiotic soup, which might then have kickstarted the origins of life. Here you also see me standing in front of a very interesting, impressive geological event. And I want to thank all my collaborators and funding agencies to make this amazing science possible. And I want to thank you very much for your attention. Thank you.